last speaker today is Damien Gaboriau, and he will speak about the measurements of Baumslag-Solitar.
Thank you very much. So I'm about to speak about Baumslag-Solitar groups from the measure equivalence point of view, and also the measure equivalence theory of their trees, their hyperbolic or non-positive curvature associated spaces. So it's a real pleasure to be here, especially because I was here 25 years ago, but I have very few memories of it. One of the reasons is that one of the organizers dragged me to whiskey bars and encouraged me to drink more than I should. It was the night before my talk. Nothing inappropriate, don't worry. But it was a terrible day, the next day. And the worst part is that this person, the organizer, couldn't wake up to attend my talk. Okay, so I guess that most of you know what I'm about to talk is a joint work with Antoine Poulain, Robin Tucker-Drob, Anush Tserunian, and Konrad Wrobel. I guess that most of you know the Baumslag-Solitar groups, this family of groups that are two generated and with one relator, and they depend on the two parameters, integer parameters, non-zero, and they have been introduced in '62 by Baumslag and Solitar. So the presentation is as written there, but I would like to write to keep it. So it's given by two generators, B and T, with the unique relation that T, B to the P, T inverse equals B to the Q. Okay, so this family of groups was very interesting. So for instance, they were presented by Baumslag and Solitar to present the first example of a two-generated, one-related, non-Hopfian group. So in particular, this iconic BS23. So you see it T conjugates a square with a cube. And so this gives a lot of complicated things. And in particular, I would like to read what Bernard Neumann wrote on the MathSciNet. So he said, these groups destroy several conjectures long and strongly held by many mathematicians, including me, he said. And it gives also, it destroys also some unpublished theorems, as well as published theorems. And I should add that this includes theorem by Baumslag and Solitar themselves. Because, you know, in fact, BSPQ is Hopfian, if and only if. So either one of the parameters is 1, so P equals 1 or minus 1, or Q, or they have the same set of prime divisors. Okay? And so this has been proved by Meskin in '72. And in their paper, Baumslag and Solitar added or one, let's say, P divides Q, which is false. So the, how to say, the curse of the Pharaoh continues. You see? So they are presented as HN extension. So you see, you have a Z and a loop with, so it's a graph of group with one vertex, one edge, and Z here and there. I mean, attached to the vertex and the edge. And so, as such, they act on their Basser tree that I call TPQ. So this is a transitive directed tree with in degree absolute value of P, out degree absolute value of Q. And usually in Basser theory, we have a base point. So, in particular, the stabilizer of this base point is the subgroup B, given the presentation as an HNA extension. Okay? And as I said, the graph of group is just one vertex and one edge, so that the group BSPQ acts transitively on the vertices and on the edges. Okay. The tree. So I said the transitive directed tree with in degree Q, out degree P. So it is the group of automorphisms of this group is a locally compact second countable totally disconnected group. Of course, the group is locally finite. And the stabilizer of the preferred vertex, say, and in fact of every vertex, is a compact open subgroup, as well as the stabilizer of this edge, let's say, of every edge. This edge, so is the edge between a root and its image under T.
So when you speak about automorphism, it preserves the orientation?
Yes, it is automorphisms of the oriented tree. Okay. Yes, directed tree. Okay. As a locally compact group, it admits R measure, of course. And the point is that this R measure is left invariant, but it is not right invariant in general. So look, here we have this edge V0, V1. So the stabilizer of this edge is Kloppen, is an open compact subgroup, and it has index Q in the stabilizer of the vertex V0. Okay, because the set of edges outgoing from V0 is a stab V0 set, and the stabilizer of the edge. So when you take the cosets, you parameterize exactly the edges issuing from V0. So it has index Q in stab V0, but it has index P in stab V1. And thus, you see that the R measure of the compact subgroup, compact open subgroup K0, that is non-zero, is Q over P times the R measure of the stabilizer of V0. Okay? And so in particular, this shows that when P is not equal to Q in absolute value, then this R measure is not right invariant. Okay? In fact, we have a modular homomorphism. So the modular homomorphism encodes the non-invariance of the R measure by right multiplication. So it is a continuous homomorphism to the reals. And in this situation, it is determined by the modulus of T and the modulus of B. I mean, it is determined by the fact, that every element in hot TPQ can be written as a product of an element in K0 and an element in BSPQ, since BSPQ acts transitively. Okay, so once you know the value of the modular homomorphism on this BSPQ and on K0, of course, it is a compact group, so under this continuous homomorphism, the image is trivial, okay? And as a corollary, of course, hot TPQ is unimodular if and only if P equals Q in absolute value, okay? Now, I switch to measure equivalence. And so measure equivalence is an analog of the quasi-isometry. When you take for quasi-isometry the characterization of Gromov using topological couplings, okay? So a coupling, I remind you, is a topological coupling is a locally compact space together with a B action of your two finitely generated subgroups, gamma and lambda, one acting on the left, the other one on the right, say, such that this action, each action is proper and co-compact. And this characterizes the fact that gamma and lambda are quasi-isometric. And Gromov then proposed this definition. So in particular, if you have two co-compact lattices in the Lie group, they are quasi-isometric. But what about non-co-compact ones?
When you say bi-action, you mean that they commute with each other?
Yes. The actions commute. So he asked, well, what about non-co-compact lattices? And so he introduced this relation, the measure equivalence. Because if you have, of course, two lattices, you can act on your Lie group by left and by right multiplications, okay? And this gives you something that resembles the quasi-isometry characterization, but of course it is not co-compact, so you have just the measure at end. Okay, so the definition proposed by Gromov in 1993 is the following. Two countable groups are measure equivalent if they admit a measure equivalence coupling, which means a standard sigma finite measure space, omega, with a measure, an infinite measure in general, mu omega, but sigma finite, equipped with a measure preserving B action of gamma and lambda, such that, well, the action of each group is free and has a finite measure fundamental domain. This makes sense? One can compose couplings. So we get transitivity. Of course, we have symmetry and reflexivity. So measure equivalence is an equivalence relation. If a group lambda has finite index in gamma, then they are measure equivalent. Okay, you just take gamma as omega, and you act on the left by lambda, on the right by gamma itself. So commensurable groups are measure equivalent. And as I said, if you have lattices in a locally compact second countable group, then they are measure equivalent. And in fact, we will see in a moment that they are measure equivalent with the ambient group itself, once we have the appropriate definitions. Moreover, if gamma lambda admit orbit equivalent free PMP, PMP means probability measure preserving actions, then they are measure equivalent. Okay, orbit equivalent actions means you have an action of gamma, an action of lambda, and you have an isomorphism between the spaces on which they act that sends orbits of gamma to orbits of lambda. Okay, it just mixes the parametrization inside the orbit, but it sends orbits to orbits. Okay. Good. So just as we have, a program of proposed by Gromov also, let's say, of classification of groups up to quasi-isometry, we have a similar program, which is of course hopeless in general. I mean, we can completely classify the groups up to quasi-isometry or up to measure equivalence. But some progress have been made since '93 on the side of measure equivalence, and in quasi-isometry, of course, a lot have been done. So one of the first and emblematic results is the following due to Ornstein and Weiss, 81. So before, and it was about orbit equivalence, in fact, any two infinite amenable groups are measure equivalent. Okay, so this measure equivalence loses the growth, the notion of growth, or the notion of ends. Z is measure equivalence with Z square. So it's a very poor equivalence relation. Yeah. For instance, also a surface group of higher genus and a free group, non-cyclic, are measure equivalent. Thus, you see you have an infinitely ended group with a one-ended group that are measure equivalent. They are lattices in the same SL2R, in the same Lie group. On the other hand, we have a lot of invariants, like Kashdan property T is an invariant of measure equivalence, unlike for quasi-isometry. Aguerreau property is an invariant of ME, unlike quasi-isometry. And we have a lot of results. So precisely 25 years ago, it was the first time I gave a talk about the fact that L2 Betti numbers are invariant. If you have two measure equivalent groups, then there exists a positive constant, C, such that the sequence of L2 Betti numbers for gamma equals C times the sequence of L2 Betti numbers for lambda. And we have a lot of rigidity results. I will just name some authors, Zimmer, Fuhrman, for lattices in higher rank Lie groups, Scott Adams, Mono Shalom, Kida. Kida proved that if a group is measure equivalent, so this is a very strong rigidity result. If a group is measure equivalent with the mapping class group of a non-stupid surface, then it is the mapping class group up to finite index, so it is commensurable to it. Okay? And so some years later, Girardel and Orbe proved the same result for UTFN, for non-stupid N. And so Orbe has a lot of work with many co-authors proving rigidity in orbit equivalence. And so what about flexibility? So we saw amenability. All the amenable groups are measure equivalent, so it's a huge class. This is a very flexible class. And by the way, this is one way to sell measure equivalence. It allows you, it is very easy to claim that from the measure theoretic point of view, a group contains Z. Even if it is an infinite torsion group, from the measure equivalence point of view, it contains Z. And so some properties that are preserved under measure equivalence or even measure equivalence embeddings allow you to consider such terrible monsters as, well, natural ones. And another property that we proved with lions is that, Russell lions, is that if a group is non-amenable, then measurably it contains a free group on two generators. Something that is, of course, not known to be not non-true for genuine subgroups. But so what does it mean from the measure equivalent point of view? This means that you can find an action, a free PMP action of your group gamma, okay, that contains the orbits of a free PMP action of F2. So you can consider that this group contains F2 for many purposes, including some purposes related to representation theory of this kind of thing that is well behaved under measure equivalence. Also, I can mention branch surfaces. that are non-obviously measure equivalent to free groups. So I mean, you take a torus, you do a hole in it, and then you take several copies of your punctured torus, and you glue all the boundary components together. This, the fundamental group of this, is not obviously, I mean, not from the usual properties. It is not obviously, but it is measure equivalent to a free group. Okay, and more generally, the same holds for elementarily free groups, and this is due to, and I do like, where is it? Ah, it's here. So it's due to Martin Brightson, Tweedale, and Henry Wilton. Okay. What else? I could mention that Tucker-Drob and Vrobel have some flexibility results on about Lamplighter groups, families of Lamplighter groups. Anyway, let's come back to our Baumslag-Solitar groups. And first classifications, so it's a very simple exercise to check that BS-PQ is isomorphic as a group with BS-QP. And also with BS minus P minus Q. Just exchange B to its inverse or T to its inverse, and that's okay. Okay? And according to Moldavanski, 91, these are all the isomorphisms. So besides this particular isomorphisms, we have no more among the families. Okay, we have 3 natural subfamilies. So if one of the parameters equals 1 or minus 1, then the group is solvable, in particular amenable. If both are greater than 1, but they are equal in absolute value, then we are in the situation where the tree has a unimodular automorphism group. So we call it non-amenable unimodular. And the third family, of course, non-amenable, non-unimodular. Okay? A classification up to commensurability has been performed by Farb and Mosher for the solvable ones in 98, and it is only in 21, some years ago, that it has been completed for the third family. And this is due to Casal-Ruiz, Duncan, Kazashkov. And you see, they are commensurable if and only if the ratio of the parameters agree. So in particular, BS-PQ is commensurable with BS minus PQ. So one can restrict to the case when both parameters are positive. Okay? And this is what we will assume from now on. Okay. Now, up to quasi-isometry, Farb and Mosher proved the quasi-isometry classification for the amenable ones. So 2 Baumslag-Solitar groups, so amenable means that there is a 1 as first parameter, and they are quasi-isometric if and only if there exist n and kl integers such that, you see, the parameters, so they are powers, non-trivial powers of the same number. Then in 2001, Kevin White proved that So first of all, F2, this is quite easily seen to be a unique class. They all are virtually Z times a free group. Okay? But White proved that they are not quasi-isometric with any group in the family F3, and he proved that in the family F3, all the groups are quasi-isometric. And this was a very surprising result at the time. I remember it was a strange family. So I will read what Moshe wrote about it. The proof depends on a powerful technique for constructing quasi-isometries, which invokes the axiom of choice via all marriage lemma. So it's a strange family of quasi-isometries. And thus, since that time, it raised the question of measure equivalence, classification to measure equivalence. So, first of all, we know that F1 consists in a single class, they are all amenable. F2, they constitute a single class because they are all commensurate. And Kida proved that no class, no element of F2 is measure equivalent with an element of F3. And then it remained the mystery case F3. And this is what we solved with Antoine Poulain, Anoush Tserounian, Robin Tucker-Drob, and Konrad Frobel. Let me give you some claims and evidences for rigidity or against rigidity. So first of all, Kida proved in 14 that if you have two Baumslag-Solitar groups in the third family that are measure equivalent, then their modular kernel, so the kernel of the image under the modular homomorphism. He proved that the modular kernels are measure equivalent. So, some hope, maybe we could distinguish the modular kernels. So, hope, nope. Kida, 10 years later, proved that they all are pairwise measure equivalent. And they all are measure equivalent with the free group of countably many generators times Z. Another result, Forrester, very recently, proved that BS k square and BS k square k to the fourth are measure equivalent. In fact, he proved that they are virtually co-compact lattices in a given, in the same locally compact group. Okay? So, again, some hope, because this is the first measure equivalence example that does not come from commensurability. So maybe we could extend this to more general groups in the family. Hope? Nope. Carrette, Cornulier, Le Boudec, Tessera proved in a paper that could maybe appear in 25, who knows, maybe later, that when P over Q and P1 over Q1 are not commensurable as multiplicative subgroups of the reals, then the Baumslag-Solitar groups are not virtually co-compact lattices in the same blah, blah, blah. In fact, they study this notion of commability. They prove that they are not commable. Okay. Last kind of results, Kida and Udeye-Raum, more or less independently, proved that if you have very ergodic conditions on a coupling. So you assume your groups are measure equivalent, so you have a coupling. If this coupling satisfies some strong ergodic conditions, then in fact the groups are isomorphic. And this condition, so very ergodic, means that the B action is ergodic when you consider the BS PQ group on the one side and any infinite subgroup of the group generated by B on the other side. Or if you want, you divide out your space omega by BS P1 Q1 and you let B act on the quotient, and you want all the finite index subgroups to act ergodically on both sides. Okay, so yet another hope. Maybe we can boost any measure equivalence coupling to impose these kind of ergodic conditions, and the final nope. So we proved, so in fact it's not a surprise, you may have read it in my abstract. So F3 is one measure equivalence class. So this is one of the rare flexibility results. And again, it's quite a surprising way that we had to explore to find this. So the conclusion is that now we have one class in each of the subfamily. Exactly one class. Okay, and for this, we had to leave the comfortable world of measure PMP, probability measure preserving equivalence, probability measure preserving actions, and we have to explore the world of measure class preserving actions or equivalence relation instead. We live a very dangerous life. Huh? We have to leave the world of discrete groups to the world of locally compact groups, and even the world of unimodular groups to non-unimodular. Okay. Good. So let me switch to locally compact groups and to give you this reformulation of Gromov's definition of measure equivalence, but which now is appropriate for also for non-unimodular groups. So we say that two locally compact groups are measure equivalent if they admit a measure equivalence coupling, by which we mean a standard sigma finite measure space. Maybe just to compare, I have here the ancient definition of Gromov. So we have a B action on the space. The B action is only measure class preserving. Measure class preserving means that null sets are sent to null sets by the group actions. Okay? And such that, so first of all, the action of G on omega is free. The quotient is nice, standard, and it admits an H invariant probability measure in the class of mu mod G. So what does it mean? On this quotient space, we have naturally a measure class. It's just a matter of defining what are the null sets. So the null sets in this quotient are those whose pre-image in omega is mu omega null. Okay? And the same symmetrically for G and H exchanged. So this definition has been, well, introduced by Bader, Fuhrman, Sauer first in the unimodular case. So it was not exactly like that, but they extended it to unimodular groups, locally compact groups. And then this definition is really due to Desprez and Lee, and most of the work has been done by Koivisto, Kuhn, and Raum. Okay, so you can check that. Again, we can compose, so ME is an equivalence relation among locally compact groups. If you have lattices, then lambda and gamma are measure equivalent in a sense because they are measure equivalent to the ambient locally compact group. Amenability and unimodularity are ME invariant. And also if G and H admit orbit equivalent free PMP action, then they are measure equivalent. And this is an equivalence if and only if when your groups are non-discrete. Also, Desprez and Lee proved that in case your groups are countable, then you recover exactly the definition, the ancient definition of Gromov. And also it is interesting to try to understand what happens for lattices. So you let omega to be G, so you have G, it acts on itself by left multiplication, and the lattice gamma acts on the other side. And so you see that the quotient G mod G is just 1 point. And so you see what it means to be in the same class. This class of measure, there are only 2 sets, empty set and the full set. Okay? What else about... Now, we turn to, since we have our preferred for this talk, locally compact group hot TPQ, there are a certain number of ME classes. How many classes? Have a guess? 4. You see, because in the amenable case, we have unimodular and non-unimodular. So we have 4 classes, and so the first 3 are quite easy to handle, and our work is really about the 4th case, non-amenable, non-unimodular. Okay. So we claim that once you have this for hot TPQ, then you have the classification for BSPQ. And the reason is just that, first of all, BSPQ is a lattice in the semi-direct product hot TPQ with R, where hot TPQ acts via its modular homomorphism. And we showed that if you have locally compact group that are ME, then their semi-direct product with R become ME. It is not equivalent, as we can see, with the amenable situation before, because these groups become unimodular, while these ones are not necessarily unimodular. If these ones are unimodular, here you just, the semi-direct products are in fact genuine products. Okay? Thus, in the family F3, you have a unique class of hot TPQ. And so this group's hot TPQ is ME with hot TRS. Thus, their semi-direct products are ME, and they contain the Baumslag-Solitar groups as lattices. And so we are done. Okay. So, of course, we have very few tools. And the most natural one is the tree itself to study hot TPQ. Okay? And so how do we proceed? So, first of all, we consider, so we have to show that given hot TPQ and hot TRS in the third family, then you consider you can produce orbit equivalent actions. This is enough, okay? So three probability measure preserving actions. So for that, so we stick to one group and we will study what we have given that group. So first of all, we consider the diagonal action. So first of all, an action, the free PMP action on some probability space, x tilde mu tilde. The measure is preserved, PMP. We consider the diagonal action of hot TPQ on x tilde times the tree TPQ. And we take the quotient. Usually taking the quotient is a bad idea because you get an ugly space. Except that here it produces a Borel space, in fact a Borel graph that is acyclic. So what is a Borel graph? So it's a huge graph in general where you have a Borel sigma algebra on the set of vertices, a Borel sigma algebra on the set of edges, and source and target maps are Borel maps. Okay. So let me explain you why it is nice. So first of all, the space of vertices in this quotient. So how do you obtain it? It is the space of vertices in the tree times x tilde divided out by hot TPQ. But you see, hot TPQ acts transitively on the set of vertices. So every pair x v admits a representative with v0 as second coordinate. This v is, let's say, g v0 by transitivity. And so this is equivalent with g inverse x v0. Okay, so in this quotient, every body has a representative with second coordinate v0. And once this second coordinate is fixed, well, it only remains k0, the stabilizer of v0, to act. Okay? And this is why we get this quotient, k0 x tilde times v0. And since this second coordinate is not acting odd by k0, we have just k0 x tilde mod k0. Okay? And similarly for edges. The group acts transitively on the set of oriented edges. And thus, in the quotient, we get something that is isomorphic with x tilde mod the stabilizer of the edge, of the standard edge, between V0 and its image under T, let's say. Okay? And of course, you have source and target maps. They are Q to 1, resp P to 1. Okay? The point is that this mixes why in the group, in the tree, you can distinguish, let's say, 3 edges out of V0. When you go to this quotient, you can no more index you cannot say this is the first one, this is the second one. Okay? And something strange is this identification here, because of course, what I did when I said the second coordinate can be V0, I could also have said can be V1. And once it is V1, the quotient is x tilde mod the stabilizer of V1, which is nothing else than T K0 T inverse. And those two spaces must be the same. They are just the quotient. They must be isomorphic. Well, just the isomorphism is a little bit tricky. Okay? And the fact that the measure is not invariant, on the right, the R measure for the group will cause certain difficulties, but this is what we will exploit. So, we have G hot TPQ acting on x tilde mu tilde, and we produced a graph. Okay? On a space, we don't know for the moment that it is nice, but look, K0 is compact, and this is a standard result in descriptive set theory. If you divide out by a Borel action of a compact group, then you get a nice space. This is why the quotient is a standard Borel space. And you can find a section of the map going from x tilde to x tilde mod K0. So there is a K0 Borel transversal. Let's call it X in x tilde. Okay, so you have this huge X, and this is the quotient x tilde mod K0, and you can find a section, a very thin space, X. But also K0 is open, so that, in fact, this transversal is a cross-section. I mean by that you look at any G orbit and its intersection with X, and you count the elements in the group that lead U inside X. This set is discrete and closed in G. Okay, so you can play the first return map game of Poincaré for real flows, you know. Okay, and moreover, you can decompose the measure. Oops, there is a mu tilt missing here. So it's to x tilde mu tilde. This is naturally in bijection with K0 times x, but also we can find a measure mu on x that makes this a measure preserving map. Okay, a probability measure. Of course, we normalize the R measure to 1 on K0. Okay. So now we have this situation. We have a transversal in x tilde, which is a K0 transversal. It meets every K0 orbit in exactly 1 point. And it is discrete. It is a cross-section for odd TPQ. And since it is a cross-section, the intersection of the G orbits with X define a nice equivalence relation, which is called the Sieber, countable Borel equivalence relation. Okay, so it's the set of pairs XY in X, for which there exists, so in the thin part, for which there exists an element in the group sending X to Y. So this is a countable Borel equivalence relation. So the classes are countable. As a subset of X times X, it is Borel. And the classes, so this is an easy exercise, correspond to the connected components of the quotient graph, T, precisely of the vertices. Okay, so our huge quotient graph, T tilde, made of V, matcal V, matcal E, is made of many, many trees, okay? And the vertices of each tree correspond exactly to the classes of EX. And moreover, EX preserves the measure class of mu. So what does it mean? It means that if you take a partial isomorphism from X to X, that sends points inside their own class. So X and phi of X belong to the same E class. Such a partial isomorphism must quasi-preserve the measure, which means sends null sets to null sets. Okay? The defect in the invariance of the measure is encoded in the Radon-Nikodym cocycle. Let's denote it W mu, so it depends on the measure. So it is defined on E, it takes two equivalent points and says, oh, this one is heavier than that one. Okay, so this is a number in the positive reals. And we claim that the class mu contains no invariant measure in, well, there is no E invariant measure. Invariant measure would mean that this phi partial isomorphism not only send null sets to null sets, but should preserve the measure. And this is not possible to find an invariant measure in the class of mu. And the terminology is E is of type 3. This goes back to Murray and von Neumann, this terminology. Okay? And there is a finer terminology, 3, 0, 3, 1, 3 lambda. In fact, we will fall in the world of 3, 0. The 3, 0 case will be our friend in this problem. Okay, so more precisely, so I said that the measure is not preserved, there is no invariant measure in the class. Along positive edges of our treeing, the Radon-Nikodym derivative exactly equals P over Q. This is not a great surprise, but okay. So we arrive eventually at the following situation. We have what we call a mu homogeneous TPQ treeing, T tilde. So it is a treeing, so a Borel acyclic graph, such that the connected components are the E-classes. In degrees P and out degrees Q, and the Radon-Nikodym derivative is exactly the ratio P over Q. Okay? And now, so this is the structure of the proof. So we have, again, cross-section, probability measure, a C-bar on the cross-section of type 3, and the mu homogeneous TPQ tree. And conversely, which means if you have an equivalence relation which is equipped with a mu homogeneous TPQ treeing, I remind you, the classes are the connected components, in degree P, out degree Q, and the condition of the Radon-Nikodym cocycle, then your equivalence relation comes from an odd TPQ action on some probability space, measure preserving via this construction. So we can reconstruct everything. And so now you see the idea. We are in a world that is not measure preserving. E does not, the equivalence relation does not preserve the measure, but it quasi-preserves the measure, and we have a tree structure on the orbits. And now we will modify the tree structure and the measure inside the class. And so we will find a suitable measure nu on X that is equivalent to mu, and modify T so as to obtain a mu homogeneous TRS, now the other parameters, treeing T prime. Okay? And for this, we have to take a particular action of odd TPQ. I mean, not that particular, but we need the action to be on a product space. So it acts first on a space in a mixing probability measure preserving way, a mixing way, and on the second coordinate, it is on a torus, on a circle, multiplicative torus, but where the other parameter appears, the positive reals mod or mod S. Okay? And the action on the second coordinate is via the modular homomorphism. We want an ergodic action, in fact, and of course, if RS equals TPQ, equals PQ, it is not at all ergodic. Okay? But it's very easy to, since it is a transitive equivalence relation, we can assume that P, Q, and RS are not commensurable. It's enough if they are commensurable, we can find a third pair of integers that are not commensurable with them, and chuk. Okay? And with this, we have this notion of associated Krieger flow that has been, in fact, introduced by Mackey. Maybe you have heard of this notion. It's also called the Mackey range. So it's obtained by, well, it's a quite standard way to produce a flow, and this is what Krieger used to classify measure class preserving actions of Z in the late 70s, I would say. Okay, and so it is known that given an action of Z, you can associate a flow, and then this is where the classification, the final classification into type 3.0, 3 lambda, 3.1 happens. And Krieger showed that every flow in return gives you, every ergodic flow, gives you one action of Z, and it is a complete invariant. Of course, we don't know how to classify flows, so it's but this is an interesting, so this is why we call it the Krieger flow. So in our situation, the Krieger flow is in fact exactly the action of, so it's a flow of the reals on the torus, the two-dimensional torus. Okay? And so in particular, EX, the equivalence relation, is of type 3.0. And so for now building this other tree, once we have arranged using the Krieger flow the measure mu to a new measure nu in the same class, then we will slide edges of T. Since it is not measure preserving but just measure class preserving, there is a way to pump edges from infinity and to add the mean value of the degree. Okay? And so step by step we enlarge, we modify the degree and arrange it to, well, for the Radon-Nikodym cocycle properties. And so we exploit a theory developed by Anush Tserounian, in particular, of measure class preserving Borel graphs. And we use this Krieger flow in a new way, in a sense. And then we reconstruct out of this new homogeneous TRS string a Borel action of the over hot TRS. That is OE, since in restriction to this cross-section, we have the same equivalence relation E. This implies OE. And that's all. Here are the authors.
Any question?
So what about subgroups of QL models? You know anything?
No. Well, we hope to obtain a whole classification of so-called treeable groups, locally compact groups. So this should be included. But of course, you have to consider whether they preserve an end or what. So it's a bit. But this should be included in the continuation. Something that should appear in 26 or maybe before the paper of Romain and his co-authors.
More questions?
Yeah, maybe I'll ask a question. I was afraid to be stupid. I felt stupid to ask it before, but now I asked Mark, he didn't know to answer, so. So maybe it's not a stupid way.
Did he drug you to whiskey bars yesterday?
I remember there is a kind of elementary result that if a locally compact group has a lattice, then it must be unimodular.
Yes.
Now, the Baumslag-Solitar group seems to be a lattice in this automorphism group of the tree.
No. In the semi-direct product.
You ordered it's equal to a product of K.
Because you see, if you the subgroup generated by B, it is contained in a compact group. So you have an infinite group generated by B. It stabilizes V0. B0, B. It is not discrete. B stabilizes V0. So it is contained in a compact subgroup. So it is not discrete.
The fact that it acts transitively on the vertices of the tree.
They are stabilizers. The action is not true. B, yeah. It is a lattice in the semi-direct product, not in, and precisely that group is not unimodular, so this is impossible. Thank you for asking the question. I'm sure many of our colleagues. Yeah, Michael?
Do you have more than 2 classes of non-unimodular groups? 2 ME classes?
Yes, we have non-trueable ones. It's a bit tricky, I don't remember the construction, but it's not easy to, but we have non-trueable ones, yes.
So this is more of just a small comment. I wanted to say at the beginning that, about when Baumslag-Solitar groups are Hopfian. So they, in fact, in this original article, they both state a theorem precisely when they're residually finite and precisely when they're Hopfian. And both those theorems are false for different reasons. And
what is true is that they are Hopfian if and only if residually finite.
Or the prime divisors are the same.
So no. And they are residually finite exactly when.
No.
Oh, sorry.
That's also wrong.
No, okay. You're right. You're right.
I had a lot of headaches with it. And
You're right.
Ness incorrect with the residual finiteness, but it's only 10 years later that Collins and Levin comes along, and they state the true characterization for Hopficity, but they don't prove it. And so 10 years later, there's a proof saying, well, here's a proof of the hard case, but they don't state the full proof, and it's horrible to find it. But at least.
So who stated Baumslag-Solitar stated a wrong proof?
They stated
wrong
both
statement.
residually finite and Hopficity.
Yes.
So it's really, I mean.
Yes, because they said either it is residually finite, and in this case we have blah blah blah,
Yes,
and this was false. Yes.
And then Mesking gives the correct proof for when it's residually finite, but says nothing really of when it's Hopfian. And then Collins and Levin give the correct Hopficity. Well, they're stated, but they don't prove it. And then the correct proof is only like 10 years later in a much broader setting about H and N extensions in general. And it's just very.
Really? And by who?
I don't remember.
I thought it was
This is the
Meskin.
case, the person who proves
It's
something.
3 authors who wrote it. 94, I think. Yeah.
Okay. Okay, thank you. So the curse of the Pharaoh continues forever.
More questions, comments? So, let's thank again.